Well, hello. Your day has arrived. The binomial theorem is finally here. If you've been paying attention to combinations, this thing is going to fall into your lap. So we're going to talk about expansions. In other words, binomial expansions. We've been dealing with that a lot. And then we're going to have exponents that are integers. But amazingly enough, we can get exponents that are rational numbers. We're used to maybe 1/2, like the square root, but how does polynomials and binomials with it's so cool how it works. All right, so first of all, let's talk about what a binomial is. A binomial is nothing more than you have two things, two terms. It's called a binomial. When you take a binomial to a power, that is called the power of a binomial. I have only heard of that once, and that's in this book. That's just weird. A problem that's going to be on your homework tonight, I thought I'd just kind of spoiler alert, is you're going to be asked to multiply this times this, and please note that bad boy. So, gosh, is there a way to kind of see the big picture and then go in and pick something that you want? That's our goal. So the binomial expansion, at some point I've asked you to multiply these things out to start noticing a few things. This is not a problem that you should have. You should be able to multiply a plus b quantity cubed and get that. If you're not, then let's get together. Let's make sure you can do that. All right. If you wanted to see it, that certainly is one way to do it. You can multiply this squared out and then distribute all those terms. I think we've, we're the A, and this is the first row, then the B, and you get that row, combine like terms, and there you go. All right, so that shouldn't be too tough. Here we go. I thought bring back some fun stuff that you haven't seen for a while. Anybody know what this is? Yes, you're all right. This is Pascal's triangle. It's a remarkable thing about Pascal's triangle is that if you take a plus b to the first, you get 1a plus 1b. No way, are you kidding me? A plus b squared, you get 1a squared plus 2a to the first b to the first plus 1b squared. Oh, no way. Mr. Sayers, you better get a thinner pen. All right. No, but 1a cubed plus a squared b to the first plus 3a to the first b squared plus a to the... No, Mr. Sayers, did that? No, we'll just go 0, huh? Maybe we can see the whole pattern. Whoa, that's so exciting. We got rid of all that. In fact, let's just get rid of that bad boy. If we take it to the fourth, maybe you'll notice that we're going to get a to the fourth. I'm going to go ahead and put b to the 0 plus a cubed b first plus a squared b squared plus a first b cubed plus a to the 0 b to the fourth. I'll bet you can fill in the last one. Yes, this is exactly correct. There is no problems, and all you need is Pascal's triangle, and what a beautiful thing. Except, what if I did a plus b to the 37th? It's big Pascal's triangle, so sometimes there's limitations, but for the first 5, that's pretty sweet. All right, so some things you should notice at this point. If you take a plus b to the nth power, we are looking left to right. The powers of a decrease by 1, and the powers of b increase by 1. Hopefully you notice that. The sum of the powers of a and b always add up to the power that we're taking it to. Well, I don't know if I remember that being, let's see, 2, 1, 2, yep, 3, 3, 3, 3, 4, 4, 4, 4, 4. Look, I haven't even written these, but I know it's 5, 5, 5, 5, 5. Woohoo! The sum of the powers, yep. The number of terms in the expansion is n plus 1. I don't understand that. N plus 1. So we take this squared and we get one term. And oh, 3 terms. Okay. So maybe I should expect 5 terms here. Let's see. 1, 2, 3, 4, 5. And that makes a lot of sense if you think b to the 0 has to be in a term, and it always goes to the b to the 4th. So there are going to be 5 terms there. All right. All right. The coefficients of the terms are row n of Pascal's triangle. So if we took a plus b to the 7th, we'd want to go to row 7 to get the coefficients. That's it. That's 5 minutes and 45 seconds. You wish it was that easy. All right. So we might be able to use this to put these together. So right now, if I gave you that, I would hope that you could find the third row of Pascal's triangle. You could go a cubed b to 0 and so forth, and you've got it. So when we have a binomial like this, all you do is substitute. So this will be our a and this will be our b, and we just plug those into the a's and b's. Sometimes it gets a little messy. I'm not scared of a few numbers. So 2x times 2x times 2x, 8x cubed. Nice job. Plug and chug. Think you can handle it? That's only 6. Oh, I'll bet there's more. All right. All right. So sometimes they get a little bit. This is a much better problem because it kind of starts you at the very beginning. So I'm showing you. Let's just kind of go back here. All right. So the first thing you'd want to do is find the 5th row of Pascal's triangle. Set up what a plus b to the 5th is. Set up what a to the b to the 5th is, and that's right here. Hopefully you notice those are alive and well. You don't see the 1 at the beginning. It's implied. It's a 1, of course. The a's go down by 1 power, and the b's go up by 1 power, so that's all nice. Make the correct substitutions. Wherever there's an a, put an x. Everywhere there's a b, plug in -2 over x. And yeah, when you get down to it, yeah, we've got some negatives, so I would say be very careful about the negatives. That's, to the first power, so we'd expect this term to be negative, and it is. We're squaring this negative. When we get x squared on the bottom, x cubed on the top. So we talked about degrees of polynomials and making sure you remembered the laws of exponents. So -2 squared is 4, times 10 is 40. X cubed over x squared, it all works out. So sometimes there's some, when you have the same variable in the a and the b, there's this combination of things, and so you don't end up with kind of exactly, in a 5th degree polynomial, you're thinking you get your x to the 5th, and it would go x 4th, x cubed, x squared, x to the 1st, and constant. But no, not when you have x's, kind of fighting each other a little bit. Because remember, we had x's in both. So just be careful. Process always works. 8 minutes. There's more, of course. All right. I had so much fun. I remember my son Coleman, who's a 10th grader now, when he was like 5 or 6, I gave him this empty, grid, and I put those first numbers down, and he filled that sucker out. I bet 30 rows. I mean, we had this huge piece of paper. It was awesome. We got them all right, which was good. But it's a pain if you have to go like 19 rows down. Because if we have something to the 19th, you would have to go down to the 19th row. Well, this is probably the most amazing thing. Put it on this side. Kind of fits. Let's try the other side. Maybe it fits better. Yeah, I think it fits better over there. Ladies and gentlemen, those numbers, maybe you've seen them before, because they are the same as when you choose something. So this 2 right here, is, you can get it from 2 choose 1. Do you notice that this is row 1? Do you notice that this is row 3? And look at the top number, 3, 3, 3. What do you think row 19 looks like? Yep, that's exactly right. The first term would be 19 choose 0. 19 choose 1. Yeah, this notation is combinatorics. There's many reasons that, there's other ways to kind of think about this. One of the most popular is if you're here, to get here, there is only one path. That's a 1. That's a 1. To get here, there are 2 paths. You could go boom, boom, or boom, boom. Here, there's 6 paths. So if you if you've ever seen those with the marble drops, it can do pachinko, I think it's called. But there's many different paths, and there you go. So the probability maybe is better that it kind of ends up there. Who knows? All right. So yay for us. We kind of made a connection to a plus b to the 5th. We can go to the 5th row of Pascal's triangle, and to tell you the truth, on an IB exam, that's what you want to do. If you have time for a quick little Pascal's triangle, get you down to the 5th or 6th row, it's almost better. Those numbers are solid. You feel good about it. You don't have to do any combinatorics. But in the general feel of it, it's really important to know that it's not just a lucky pachinko ball that the numbers land up. In fact, it's almost I don't know why this book says, hey, look at this, look at those numbers. It's really an observation of combinatorics that give you this 1, this 5, this 10, this 10, this 5, and this 1. Okay, so I'm going to show you why that is. When you multiply 2 binomials, you are picking one number from this and multiplying it times one number of this, writing it down. And what you have to do is you have to come up with all possible combinations. So the real famous thing here is to say FOIL. So first, outside, inside, last. So that's a really popular one until you don't have 2 binomials. Then you're FOILed. But basically, you picked one here, you multiply it times one here. You picked one here, you multiply it times another one. In other words, you kept up and figured out all the possibilities. So what happens when we move to bigger and better things, like we have 5? So when you multiply this out, you basically are taking on the task of picking one here, one here, one here, one here, one here, and writing down your answer, and then going back and picking one here, one here, one here, one here, one here, and so forth until you've come up with all the combinations. Like maybe you go A, B, A. Okay. Now we can kind of look at this. If I want A to the 5th, how many choices do I have here, 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 and here? Or I think it's almost better to think in this first one, B to the 0. So if I want to get 5 A's and 0 B's, if I have 5 to choose from here, and I need to pick 0 B's, I get 5 choose 0, which is equal to 1. There's only one way to get A to the 5th, B to the 0, and that's if I pick that A, that A, that A, that A, that A. Let's go to a more interesting term. How about A squared B cubed? How many ways can I choose 2 A's out of the 5 binomials? Do you hear the language? How many ways can I choose 2 A's out of the 5? Well, I can do 5, choose 2. And that certainly is 10. But another way I could do that is 5, choose 3 B's. So does it matter which one I say I'm choosing? If I pick the two A's or the three B's, I'm basically separating that group into the two A's or three B's. However I count that is going to be the same. And if we've only had a day, but to notice that there's some symmetry about this is really important. In fact, let's take a picture of that, or look at that. Notice the 5 choose 2, and the 5 choose 3 give you the same. 5 choose 1 and 5 choose 4 give you the same, because how many ways can I pick one person is kind of the same thing as how many ways can I leave 4. I knew you'd catch on. Very good. All right, so what does that mean to us? What does that mean to us? Well, my good friends, we have what we call the binomial theorem. All right, there's a lot going on here, so let's kind of look at one thing. If we take this to a power, notice, kind of separate it. Notice we have a to the n, b to the 0. We have a going down by 1, and we have b going up by 1. I wish they gave the next term here, because it'd be a to the n minus 2, b squared. So you'd really see that b increasing and the a decreasing. This is what we call the general term. It's like we kind of write it in there because it's like in the middle. And it's like, I don't know, how far is it? We don't know what n is. But at some point, we know that a is going to be the sum power, and b is kind of has to be that complementary power, so that when these two add up, we always get n. Remember, those two have to always add up to give us that power of n. And the a is going to continue going down until it gets to a to the 0. So this is a to the 0, b to the n. Now, what's happening in front is that coefficient. Unfortunately, they think, oh, they don't need to see the coefficient. I think you do. Let's be solid and make sure this is n choose 0. Remember, there's one way to pick 0 things from n objects. And and the same thing goes over here. And then n choose 1, n choose 2, n choose 3. And then here is that magical, you pick the numbers and you put them in, they'll work. So whenever we write a big summation, we haven't done this, maybe you did a lot in calculus, I'm hoping you did, we can use sigma notation. The way sigma notation is, we plug in 0 for r, n stays the same, so n's a constant, but r goes from 0 to 1 to 2 to 3 to 4. We plug it in here and we create all these terms. That's why we call this the general term, because as r changes, that takes on that form. A little reminder, that notation, the common n choose r is the same thing as n over r, n factorial, r factorial, n minus r factorial. All right, let's do some problems. Write down the first 3 and the last 2 terms of the following binomial expansions. So if I were looking at this, or maybe you think of this as my a and this is my b. I know the first term is going to be 11 choose 0. That my a value to the 11th and my b value to the 0. Do I need to write all that? I do, especially when I'm trying to learn it. That's the first term. And then everything's a pattern. 11, this goes up by 1. We get 1 to the 10th, and we get 2x to the first, plus the next one, 11 choose 2. 1 to the 9th times 2x squared. And then if they want the last 2, maybe I do dot, dot, dot. All right, the last 2. So it's going to be 11 choose 10. 1 to the first, 2x to the 10th. And then 11 choose 11. 1 to the 0, 2x to the 11th. So it's all about patterns. It's all about not worrying about what a and b represent. It's just writing them down. And if you wanted to clean this up, 11 choose 0 is 1, 1 to the 11th is 1, 2x is 0. So the first term is 1. That's what you're going to see in the back of the book. Plus, I know this is 11 times 1 times 2x, and that's going to clean up to be 22x. And 11, 2, 9, 10, 55 times 4, 220. I'm thinking that's 220 x squared. That's a guess. I'm not going to do the other one because I think you got it. I think you just got to go slow and get your n's and your r's right and finish that bad boy out. I don't think I'm going to take the time to prove this. I would start with a plus b to the n is equal, write it. I would substitute a plus negative b to the n and sub negative b in for b and see if you can work it out to get that. Bet you can. All right, write down the general term of the expansion. So this is important to me that you kind of go, okay, the general term is going to be n, choose r, a to the n minus r, b to the r. Always, 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 always start there. I believe that's in your formula packet. So how do we, what do we write? We know what 8 is, or n is. We don't know what r is. Remember, it's a general term, so this, I can pick what my r is going to be. A is going to be x, 8 minus r, and b is going to be 2, and that's going to be r. So do you see that I can pick r equal to 4? And I can plug it in, and I'm going to get 8 choose 4. It's a number. I get x to the 8 minus 4, or x to the 4th, and 2 to the 4th. And I get my general term. Just a term. Ooh. So find the coefficient of x to the 5th. And I don't want to multiply this out. So the question is, could you pick a value for r so that I will end up with x to the 5th? I really hope so. But it's a really easy question to answer, but you got to ask yourself the question. You've got the general term. I can pick r equals 0, 1, 2, all the way up to 8. And when I do that, I pump out all the terms. But I don't want to randomly pick numbers for r. I want to pick a value for r so I get x to the 5th. Well, I hope you recognize that when r is equal to 3, that is going to give me that x to the 5th. So 8, choose 3. X to the 8 minus 3, 2 to the 3rd. So 8, choose 3, x to the 5th, 2 cubed. Maybe we finish this with 8, choose 3 times 8, x to the 5th. So right here is the coefficient. Yeah, if I had a calculator or this amazing brain that, I could do it. Is it 56? I think it's 56. 7 times 6 times 8 times 7 times 6. Ooh, no, because it's 5. Yeah, 3. Yep, 56. 56 times 8 is 448. I'm going to guess 448 x to the 5th. But rely on your calculator. All right, write down the expansion of something, something. Write down the general term. So A, I hope I'll repeat myself. N choose R. A to the N minus R. B to the R. So our general term is going to be 12 choose R. A to the 12 minus R. B to the, come on Sayers, you got it, R. Oh, darn it, I shouldn't have used A, so I'll do one more step. 12 choose R. A is x over 2 to the 12 minus r, and 1/3 to the r. That's your general term. R can be values from 0, 1, 2, all the way up to 12. Which one should we do? Should we do x to the 9th? So, what contributes to x to the ninth? Does this? No. Does this? No. Does this? Yeah. So some of these are going to be straightforward. Focus on what you want. We want x to the ninth. What would r have to be for that to be a 9? Because it's x to the first. So x to the first to the ninth will give us x to the ninth. And again, it is r equal to 3. No, r is not always equal to 3, but it is in this random case. So 12, choose 3. X over 2 to the ninth and 1/3 cubed. But we want the coefficient, so I'm going to factor out the x to the ninth. It's all the numbers that are left that are really the coefficient. So that was delayed, and that was unfair. 12, choose 3. Don't forget that 1/2. 1/2 to the ninth and 1/3 cubed x to the ninth. I know I'm going to get x to the ninth. I don't have to make a big deal out of it. Just pull that out front. All right. Are we done? Is it? Oh, no? All right. Ooh, okay. So this is where HL comes in. I think a lot of people with a little practice can do those problems. We're going to do this one. Find the coefficient of x to the 6. All right. It doesn't ask you to get the general term. Baloney. Write the general term always. Okay? Maybe you can go a little faster. I'll go 12, choose r, x squared to the 12 minus r, and 4 over x to the r. R can be anything 0, 1, 2, all the way up to 12. All right. We want x to the 6. What contributes to the power of x? Does this? No. Does this? Oh, yeah, it's got an... Ooh, we have two things kind of vying for it. So the way I like to do it is I like to get rid of all, if there's like numbers like this 4, I'd like to just kind of forget about it. So I do this. X squared to the 12 minus r, and watch this. I'm going to drop the 4. All I'm focusing in is trying to figure out what that r value is. So I'm going to write this as x to the negative 1 to the r. Okay. And what do I want? I want x to the 6. So this is the focus move. Focus. Don't even worry about the numbers. We're trying to flush out what r is. Well, welcome to pre-calc. This is where you worked on your exponents. That's x to the 24 minus 2r times x to the negative r equals x to the 6. When you multiply the same base, you add those. So x to the 24 minus 3r is equal to x to the 6. When you have the same base, you can set those exponents equal. 24 minus 3r is equal to 6. Negative 3r is equal to negative 18. And r equals 6. All right, I will tell you right now, if r equals 6.378, what that's saying is there is no term with that x to that power. So if you do this process and you don't get a whole number here, it's not saying you messed up, it's saying that there's no term with that x power. So r equals 6, now we go back, now we go get the coefficient. So, of course, change maybe to, I don't know, who should we go? Green? It's not easy being green. Ooh. Okay. All right, so we know that what? R is equal to 6. So now we just plug it into here and see what we get. I'm going to try to write it over here. So it would be 12, choose 6. That's a number my calculator can do. X squared to the 12 minus 6 is 6. And I'm going to write this as 4x to the negative 1 to the 6. So r is equal to 6. There's two things to check here. There's two things to check. One is, do we end up with x to the 6? So 12 choose 6 is a number. We're going to get an x to the 12th here. We're going to get a 4 to the 6th x to the negative 6. And sure enough, that's going to end up with an x to the 6. And our coefficient is 12 choose 6 times 4 to the 6 times x to the 6. There's too many 6's. That's it. So don't freak. Just because you got two x's kind of vying for it, this is the key step. You got to focus just on the x's and then come back to get the coefficients later. All right. We're bordering on 30 minutes here, so I'm going to do one more. The constant term, that is such a cheap way. I hate that because we study this so hard and then all of a sudden they use that in the IB exam and now they ask the question. The constant term is saying what is the coefficient of x to the 0? What is coefficient of x to the 0? So it's up to you which one you want to do. Maybe, I don't know. You want to do, let's do B. All right, so how does B work? First of all, the general term, that's going to be 9, choose R. That's going to be x to the first, 9 minus R. That's going to be negative 3x to the negative 2 to the R. Do you need to pull the x up? No, I just like it. So now we're going to focus. So we get x to the first to the 9 minus r. We're going to get x to the negative 2 to the r. And we're going to make that equal to x to the 0. Mr. Sears, where'd the 3 go? It didn't go anywhere. We don't need it when we're just trying to find the exponent of x to work out. We'll get r and then we'll plug it back in. Don't freak out. Don't panic. Okay. So that is, oh, you little sucker, you. That is x to the 9 minus r times x to the negative 2r equals x to the 0. That's x to the 9 minus 3r equals x to the 0. That is 9 minus 3r equals 0. And I think in most circles, that is going to be r equal to 3. So we plug in r equal to 3 into our general term. So that is going to be 9 choose 3. That's a number. It is going to be x to the 6th. I can't get away from it. And it's going to be negative 3 x to the negative 2 to the 3rd. We're going to get it again. 9, 3, x to the 6th, negative 3 to the 3rd, x to the negative 6th. And that's what we expect is we get x to the 0. 9 choose 3 times negative 3 to the 3rd. X to the 0. You don't write x to the 0. You just call it the constant term. 33. You can call this whenever you want. So don't complain to me about too long. I think you got, these are kind of the same. Some are a lot easier. Like these, ooh, you know, you got a tricky, but those, you know, you got an x squared, you got to be careful. So, but x squared to the what will give me x to the 10th, probably the 5th. Ooh, all right, so I'll let you kind of mess with those. Yeah, those are kind of challenging, but maybe get out of your way. All right, let's do this one. This, I think, is basically, no, I think, yeah. I promised you one problem, and it's this one. We're going to do this one. All right. X to the, what is up with x to the 6th? Oh, man. So, this is a big polynomial, and then we're going to multiply everything in that polynomial by this. So it's like, what? All right, here's the key. 2 minus x, we're going to multiply it times this polynomial. I don't want to go to the 9th row of Pascal's triangle, plug in the a of 3x, the b of 1, and figure all this out. So really, maybe the key is I should figure out what terms are going to kick out in x to the 6th. Remember, I'm going to multiply all these terms by 2, and I'm going to multiply all these by negative x, and then I'm going to combine those. So the question is, what term would I be multiplying 2 by in order to end up with an x to the 6th? Well, it's probably x to the 6th. What term would I be multiplying negative x by to get x to the 6th? Probably x to the 5th. So I hope you can understand that what I'm really after here is I really need to get this term and this term. And once I have those, I need to multiply them times these two little deals to kick out all possible x to the 6th, since that's the theme of the party. X to the 6th, combine those, and I will get my final term. So let's do it. So I'm going to focus in on 3x to the 1st to the 9th. I need the coefficient of x to the 6th. I'm going to do this a little faster here. 9, choose r, 3x to the 9 minus r, and 1 to the r. When these are just x to the 1st and there's only 1, it's pretty easy to notice that it is going to be r to the 3rd, or r is going to be 3, because 9 minus 3 is 6, x to the 1st to the 6th, that's going to be good. So that is 9, choose 3, 3x to the 6th, 1 to the 3rd. Yeah, of course you're not writing the 1, but you know, 9, choose 3, 3 to the 6th, x to the 6th. All right, so that's x to the 6th. Now we're going to do x to the 5th. That's going to be, I'm going to use the same, I don't have to rewrite this. So what would r have to be so I get an x to the 5th? It would be 4. So r would equal 4. So I plug that in, I get 9, choose 4. 3x to the 9 minus 4 is 5, and 1 to the 4th. All right. So ladies and gentlemen, this is this term, and this is this term. So now all I have to do is multiply this 2 times the x to the 6th term plus I need to multiply that negative x times the other term leave the 1, and I'm going to get a number, and it's going to be right, and we're going to be psyched. We're not doing another problem. What do you think about that? Can you do it? Can you handle it? Do you see that? It's totally doable, but it's like you got to be organized. Wow, 39 minutes. What a great weekend for you. All right, I'm going to keep this under 40 by telling you that this is really it for the whole chapter, this section. So we'll spend 2 to 3 days really basically practicing this. I want it to be fluent. Tomorrow you'll start the homework. Probably won't have time to finish it, but I'll give you more time the next day. All right, thank you.